Hello, sir. I'm going to give my presentation on how process and thread synchronization works in Windows XP. First, we'll see why exactly we need process synchronization, then what it exactly is, and then how it is handled by Windows XP. Okay, processes or threads can run concurrently and may be interrupted at any time, completing the execution partially. This can lead to the following problems like conflicting access to shared memory, race conditions, starvation, or even deadlocks. Now, process synchronization. A process may need multiple threads to share some data. If access is not controlled to be sequential, then the shared data may become corrupted. And that leads to many inconsistencies and stuff like that. One thread accesses the data, begins to modify the data, and then it is put to sleep because its time slice is expired. The problem arises when the data is in an incomplete state of modification. Another thread awakes and accesses the data and is only partially modified. The result is very likely to be corrupt data. Process synchronization means sharing system resources by cooperating processes in such a way that concurrent access to shared data is handled carefully, removing inconsistencies. There are a variety of ways to coordinate multiple threads of execution in multi-threading environment. Let's say a process has four threads which needs to access and manipulate a single thread, a single shared global variable x. Threads need authority before they can interact with x. It must also agree with all the threads that it has the right to use x. While the thread is using X, all other threads must wait or sleep for their turn. If multiple threads all want to access and use X at the same time, there must be a mechanism to ensure that only one thread can access X at a time. This kind of activity is called locking for threads. There are a lot of ways to support how to use shared resources such as critical sections, mutexes, and semaphores, events, and atomic operations. Synchronizations in Windows XP. To avoid race conditions and other synchronization problems, it is necessary to synchronize access by multiple threads to shared resources. Synchronization is also necessary to ensure that interdependent code is executed in the proper sequence. Windows gives us these synchronization objects which help us to synchronize various processes and threads. Each synchronization object instance can be either a signaled or non-signaled state. A thread can be suspended on an object in a non-signaled state. The thread is released when the object enters the signaled state. The mechanism basically is that that process or that object can be active or inactive. While it's active with another thread, no other thread can access it. But while it's inactive and it has no other threads, all the threads which need to access it will like one thread will be chosen amongst all those threads which will access this object then. The following table lists examples that can cause object types to enter the signal state and the effect it has on waiting threads. Like for the process, when the last thread terminates, it goes into this signal state when it is ready to be used by other threads. Or in a semaphore, when you know that the number of threads or processes using this resource goes down for a certain threshold number, then a certain threshold number, and other processes or threads can use that information. Now, synchronization objects. Synchronization object is an object whose handle can be specified in one of the wait functions to coordinate the execution of multiple threads. More than one process can have a handle to the same synchronization object, making inter-process synchronization possible. In Windows Win32 programming, the following object types are provided exclusively for synchronization, like event, mutex, semaphores, waitable, timer, and critical section. Now, the wait functions. The wait functions allow a thread to block its own execution. The wait functions do not return until the specified criteria has been met. This type of wait criteria determines the set of the criteria used. When a wait function is called, it checks whether the wait criteria have been met. If not met, the calling thread enters the wait state until the conditions of the wait have been met or the specified time out interval elapses. There are four types of wait functions: single object, multiple object, or alertable, and registered. Single object wait functions. The single object and wait for single object and wait for single object ex functions require a handle to synchronization object. These functions return when one of the following occurs. The specified object is in the signal state, the timeout interval elapses. Multiple object wait functions. Wait for multiple objects, wait for multiple objects, ex, and etc. Functions enable the calling thread to specify an array containing one or more synchronization object handles. These functions return one of the following when one of the following occurs. The state of any one object specified in is set to signal, or the state of all the objects have been set to signal. The timeout interval elapses. Allowable functions. The MMSG wait for multiple object X and other functions like this differ from the other wait functions in that they can optimally perform an all allowable wait operation. In an allowable wait operation, the function can return when the specified conditions are met, but it can also return if the system queues and IO operation. Registered wait functions. The register wait or single object function differs from the other wait functions in that the wait operation is performed by a single thread and the wait pool and a thread pool when the specified conditions are met. The callback function is executed by a worker thread from the thread pool. By default, a registered wait operation is a multiple wait operation. Mutex objects. A mutex is a recursive lock with behavior similar to critical section. A thread must own a mutex and other request access. Again, is immediate granted access. An owing thread must release a mutex the same number of times it requested ownership before the object thread can become the owner. Mutex objects can have the following additional features. A timeout can be specified for the function to access a mutex. When the mutex is created, there is an argument that specifies whether the thread that created the mutex is to be considered as the initial owner of the object. If a thread terminates while owning a mutex, the mutex is considered to be abandoned. When this happens, the system will grant ownership of the mutex to the waiting thread. Semaphore objects. Now, semaphore works in this way that you can assign a particular resource a semaphore, and the maximum number of processes which can actually access it at the same time. It keeps a check on how many processes are accessing this resource. If that number goes higher, it doesn't allow the additional processes to access this resource. Waitable timer objects. A waitable timer object is synchronization object whose state is set to be signaled when the specified due time arrives. A thread can be cancel waitable timer or function to set the timer in inactive state. To reset the timer, call set waitable timer. When finished, the timer objects call close handle to close the handle to the timer object. Event objects. The event object is a synchronization object whose state can be explicitly set to the signal by use of set event. There are two types of event objects: manual reset event and auto reset event. Critical section objects (CS). A CS is essentially a Win32 version of recursive mutex lock object. If a thread calls leave section, it will when it does not have ownership of CS, an error occurs. When an error occurs that may cause another thread using enter critical section to wait indefinitely. Unlike a mutex object, CS is not a kernel object and can't be shared across processes. Fact that mutex object are kernel objects means that CS may be faster than mutexes. Other methods of synchronization, condition variables is one of them. One-time initialization is one of them, and then there are timer queues and interlockable single linked list. An interlockable single linked list (S list) eases the task of insertion and deletion from a linked list. Lists are implemented using a non-blocking algorithm to provide atomic synchronization, increase system performance, and avoid problems such as priority inversion and lock convoys. Interlocked variable access. The interlocked functions provide a simple mechanism for the synchronization access to a variable that is shared by multiple threads. They also perform an operation on variable in atomic manner. The threads of different processes can use these functions and variable is in shared memory. And then of course there are synchronization barriers. Well, thank you a lot for listening to me and being patient during this presentation. Thank you.